Hey everybody. Thank you so much for coming to Wasm Whiplash, WasmCloud's Wild Ride to Standards. This is actually my first talk in the maintainer track, so super excited to be here talking to other maintainers. I hope that this is informative and inspiring for you, as it is a therapy session for me to talk about our past mistakes and a wild ride over the last 5 years of working on WasmCloud. I'm a senior software engineer at Cosmonic. I'm a CNCF Wasm Cloud maintainer, which is now an incubating project. I've been with the project since its conception in 2019, coming out of Capital One, a huge rustation, and a big and very sad demo enthusiast, because I actually have no demos for you today. It's my first time ever doing that, so I'm going to try to hold your attention, and hopefully this should be fun. The last 5 years of working on this project. So for today, going through the agenda, I want to talk just a little bit about what Wasm Cloud is, why it exists, the origins, the ideals, why the project started in the first place, what we built that differentiated us, and what we built to even show up as a project in the space using a new technology of WebAssembly. I'm going to talk about the standards that solved so many of our problems, and just in general, standards and why they matter. Now today, Wasm Cloud is an incubating project in the CNCF. We're a Wasm-native application platform for deploying applications everywhere. We use WebAssembly as the unit of compute rather than a container for an application, which means that you can compile your code to this platform-agnostic, tiny binary to any cloud, edge, even your own. Now, just like containers need container-native platforms to do their best work, orchestration, all of the things that you see here at this conference, WebAssembly needs the same thing. It needs Wasm-native tools, and that's what we've been providing for quite a long time. But before we can think about where Wasm Cloud is now, we need to take a little bit of a step back. Let's go all the way back to 2019, where we started. And before Wasm Cloud was Wasm Cloud, it was actually called Waxosuit, a cloud-native exosuit for WebAssembly. And I know what you're thinking, that is the coolest name, and this is the coolest logo, and that this talk is going to be all about the mistake of renaming to Wasm Cloud. Unfortunately, that is not exactly where we're going to go, but I understand you all are welcome to take the name. Now, this project wasn't created to use WebAssembly as a technology. Like, we didn't start Wasm Cloud because we were like, we got to use WebAssembly on the server side, and we're going to be the ones to do it the best. We started because we saw the pain of making microservices at a large enterprise. There's a ton of boilerplate and copy and pasted code from these golden blessed templates and container images that you're allowed to use to deploy your application. You just copy and paste it from each one, meaning that when there's a vulnerability in one of those nice templates, every single application team has to go roll their application, rebuild it, redeploy to production, and that causes a ton of friction. It's what developers spend a ton of time on, and that is not enjoyable or productive at all. Now, this is something that we wanted to address when we started the Waxosuit project. And the strategy was really per application, we are bundling in so many different things that are not just the application code, not just the things that the developer writes and ends up using for their features at the end of the day. It's all the open source dependencies. It's all the capabilities like using HTTP or having like your enterprise specific distributed logger. And it's also information about the platform that you're going to be running on. You know that you're going to be running and building to a container. You're going to deploy it on Kubernetes. You need this service and this service account and this ingress. And it's all these things that you need to know about the platform you're deploying on that's not just the developer responsibility. So our thought is if we can make a project where the application code was the only thing that was in your actual unit of compute, the only thing that a developer had to write, maintain, and deploy to production, and leave all the rest of the management of dependencies, the run ops, the capabilities, all those things, if we could push that into the platform, then that allows the platform engineers to have control over that, offer it to developers. Developers just write code. Whatever language, doesn't matter. And picking WebAssembly as the unit of compute was a bet that the foundations of WebAssembly that made it so successful in the browser would make it successful on the server side. We certainly could have approached this in a different way. And looking at WebAssembly as a technology in 2019, There were definite pros and cons. Some of them still apply today. The pros, it's an open W3C standard. At the time, it had shipped in all major browsers. I think it was March of 2019 that WebAssembly 1.0 supported in Chrome, Safari, Firefox, the other one. We had secure sandbox execution, platform-agnostic binary, small size, near-native execution speed, and it's just a binary target. So you can compile to it from any language theoretically, as long as it supported the WebAssembly instruction set. These were all the things that had to happen for it to ship in the browser. And we're looking at this, and it's like, this would be great for cloud-native microservices. If it was a tiny binary that was secure by default, you can write whatever language you want. Sounds kind of nice. Now, there are definitely some, wow, I have pros and pros on here. Wow, you all noticed it. Nobody said anything. Pros and cons. Some of the cons is that because the support shipped for the browsers, a lot of libraries that supported WebAssembly assumed you were going to run in the browser. So it would have like JavaScript glue code in there, and that wouldn't work for running on the server side. As far as what can go in and out of WebAssembly, it's only numbers. So you can write functions that you can call from the host or from the guest that can take in numbers and return numbers. That's it. No strings, no lists, no arrays, nothing. And when it comes to networking support, all of that has to happen over the same ABI. So how are you going to deal with pushing a bunch of bytes over a socket if you're just passing like two numbers back and forth? It's a little harder. If we zoom in a little bit and just kind of think of WebAssembly a little more holistically for the folks. Actually, I usually do this survey. How many of you have heard about WebAssembly here? Okay, so pretty much everyone. How many of you have like written something, compiled it to WebAssembly, and like done something semi-useful with it, even if it's just local? Awesome, nice. So for any of the folks that haven't really heard of this technology before or are looking to grasp it, the best way to think of it, just at its highest level, is WebAssembly is a guest in a stack-based virtual machine. So you take code from a source language, a guest language like C or Rust or Go or Python, you compile that to a WebAssembly component, WebAssembly module, and then that is the guest that runs in the host virtual machine. And that is implemented in all major browsers. It's implemented now on the server side, things like that. And then it works on any supported architecture. Now, this may sound a little similar to the Java model, where you have Java code and you compile it to a jar and then you run it on the Java runtime environment. And it is a lot like that. It's just not like only Java. And WebAssembly people hate it when you say this. So if they ask you, you should tell them this, and this is how you understand it. But if you think of it kind of like the Java model, that works too, right? So when we think about these interacting with a WebAssembly guest from the host, or you're writing an application, you're interacting with the host, you can only take in and return i32s, i64s, f64s, f32s. And that's it. And so when it comes to that limitation, there's a strong reason for it. It's very simple to implement just number back and forth communication with a guest. It's very simple to implement on the runtime side. Guest languages are free to have like a higher level abstraction for this. But it does very critically assume shared memory. And that is how essentially a lot of the WebAssembly ecosystem worked for quite a long time, is you would like have a slice of bytes in the WebAssembly memory, and the host would have to read that in response to what you're doing. So this is obviously a lot lower level than the average developer is trying to go out. And I mean, I would say like 99% of developers are trying to go out and like write a microservice. You're not going to be like, all right, you know, now I'm going to pass my numbers back and forth. And that's where the WebAssembly system interface, or WASI, came to be. So this started as a way to create secure standard interfaces for writing applications that can be run in the browser, that can be run on the server side. And it's supposed to create a foundation so that language tool chains can target a standard. You know, this is things like writing to a file descriptor, accepting a socket, reading an environment variable, like the POSIX style things that you could do in an application. And this started, this started all the way back when we were beginning with WasmCloud. But ultimately, we looked at this and we thought, well, we're not trying to do something that's POSIX. We are trying to make a different style of microservice. So the standard that's emerging, it probably won't work for us. So we were looking at ways to compensate for the cons of using WebAssembly in 2019. Instead, to compensate for the numbers in, no numbers out, no complex data types, we said, all right, we will write an FFI protocol across WebAssembly, the binary guest, and we can actually pass complex types around by serializing them to bytes and then passing a pointer and a length to read. It's like, comp 110, like the first thing that you do. Instead of trying to create special ways to do limited networking support, we can use native binaries, which already have the support for that, or even containers, and we can just have a way for these distributed, the WebAssembly and these binaries to communicate over a distributed protocol. The polyglot support only really works if you use the same API, so we'll write language-specific SDKs so that it can match our binary protocol, and we'll just use the totally target triplet WASM32 unknown unknown to compile to, so we don't assume any environment. It's basically just bare WebAssembly compute. So first thing, as we start on our journey to help developers be less frictionful when they write applications, is to create our binary protocol, which is WAPC. So this is a whole protocol where the host can invoke a function on the WebAssembly component and pass it a bunch of bytes, and then the component could like call back and say like, hey, I had this error and you should probably read it from this place in memory. And then the host can be like, well, okay, well, I have an error actually, and you need to read it from this. And this is like so much, right? And it actually worked really well. Right? We used it for about 4 years to pass complex types using WebAssembly. And really, if you look how complicated this is, really what this means is that every language that we wanted to support for WasmCloud, we had to write an SDK in that language, implementing this protocol, using that language's memory models. And most importantly, this is an open source project, and WAPC still exists today, but this was proprietary to that protocol. If you were writing an application using our open source project, and you were trying to compile the WebAssembly and do what we were doing, you were now tightly coupled to our platform. You had to use our project. You can't take that and go anywhere else. You have to rewrite it, basically. So really, this is the same model that happens all over the place, right? You have a lower level API, and if we can all kind of agree on a nice lower level API, then we can write higher level APIs to target it. Things like glibc, and then that goes down to syscalls, which is another API that we've all kind of agreed on that looks kind of nice. So there's an evolution of this. So we started from the bottom and worked from the ground up to build our own guest SDKs. So we did it in Rust, we did it in Go, we did it for TypeScript, we did it for Zig, Swift, and every single SDK implements this binary protocol, and then you just have to serialize your complex types to bytes, and then on the other end, you do the deserialization too. A little annoying, whatever. It all works, very generic protocol, it's nice. Now the problem is we started writing a bunch of extensions, things that you could do with WebAssembly, like to make HTTP requests, and we assumed that we would just like serialize the complex types to JSON. So everybody can just deserialize that from JSON, or maybe we would use message pack, like a complex, or a standard, but it's an assumption, and then that means that every single person has to use that same serialization format. So we're like, all right, maybe that would be a little hard. So why don't we use an IDL? Why don't we write some codegen? And so this will work in every single guest SDK. We just need to write a codegen module for that language and generate some code, right? Instead of hand coding it, we've got the protocol, so people can define their own complex types, like saying hello world, and then go from there. So we tried our own. We called it WTEL. This was another one of our awesome naming decisions. It was a WTEL cool. You can see that on the left. This is how you would write a hello world. It's fine. It's pretty understandable. But then we were maintaining our own IDL. Like we wanted to represent like recursive types, and now we have to update an IDL, and we have to update our codegen. This may sound so obvious to you now that I'm saying it out loud, but then we were like, okay, this is way too much. Why don't we use a well-established IDL that like people use? And we looked at a couple things. We looked at like Captain Proto. We looked at protobuf, and then like that, you have to put your protobufs everywhere. This is not a protobuf rant talk, so I'm gonna leave it for later. So we were like, okay, we're gonna use Smithy. How many of you have heard of the Smithy IDL? Nice. 2? Awesome. Smithy is what Amazon uses to describe all of their AWS services internally. So they use the Smithy IDL, they can generate code from that, and there was actually like a Rust and some support for the different languages that we wanted to use. So we're like, we're going to use an established, like, Amazon did. Like, this is going to be great. And so we do all of this, right? And if you really just like step back and take a break, what I've been talking to you about for the last like 10 minutes is all the stuff that we built just to like get here. And the things that we actually got to work on at this point, the really exciting pieces in Wasm Cloud that set us apart at the time were really interesting. We were doing a distributed network of computing with a flattened topology network using NATs like the CNCF project, so that you have these WebAssembly binaries. They could be running on any cloud, any edge. We get automatic failover. They can communicate the same as if they were running locally. We have loosely coupled contracts, so you could actually have like a database connection or a key value store implemented for Redis locally, and then you could just swap that to use one that targets DynamoDB when you deploy to production. We can run our actual host as a binary, or you can embed it in your own system. We have a signing mechanism, networking, the distributing of these WebAssembly components, weekly WebAssembly community calls where we're bringing everybody in, and it was so cool to work on these parts of the technology, and this is what sets us apart as Wasm Cloud. But we had to build all of this stuff just to even show up in the ecosystem, and we spent a long time maintaining it. We wrote raw PC and then all those codegen libraries, and then we switched to a new IDL, and so we wrote a different codegen library, and now that we were maintaining that, and it's just so much churn where we're rewriting things and trying to adopt things, but we're spending all this time on stuff that's really not making our project better or different. And I think all projects can fall into that pitfall. And when you look at what we're really missing, we didn't really need that much. We just needed complex types to go across the WebAssembly guest host binary. We need to represent that and be able to pass complex types around. We're not doing hello world with a pointer and a length to read from a byte slice. We're doing hello world by handing you back the hello world string. And we wanted idiomatic experiences in the own languages. And there are even clever hacks that people will do today, but if you take anything away from this section of the talk, every single WebAssembly project that uses WASI or WASM32 unknown that has things that are more complex than passing numbers back and forth is doing it in their own proprietary way that locks you into their platform. You have to use their interfaces, and if you want to write WebAssembly and target something else, like the browser or whatever, you better hope they have an SDK there, or you're going to rewrite it. That still happens today. There are great reasons for it. I'm not trying to throw shade on people who are using WASI Preview 1. It's just the thing that if you're saying that you've got all this awesome support, it is something that you have written as a project to do that in your own special way. There are even like super clever hacks that people are doing now to make this even more efficient. And really, the years and years of people doing this in their own way led to people saying, well, hey, we really need this to happen, and we'd like it for it to be a standard. And from these proposals came, from WASI Preview 1 or WASI 0.1, WASI 0.2. And there are two core proposals to the foundation of WASI 2. The first one is interface types, which is a way to represent complex types in WebAssembly when passing back and forth between host and guest. This includes an IDL that brings the assumptions and the things that you need to know about WebAssembly along with it. Code generation for guest languages, which can be implemented by like people who work in Go all the time. They're gonna be like, well, hey, this is how I want it to look when I generate like a complex type. I want it to come out as a Go slice, not this weird thing. And it also allowed for creation of standard or custom interfaces without changing the entire WebAssembly specification. So we can ship a set of interfaces for what it looks like for WebAssembly to be a CLI, to like execute it on the command line, or for it to be an HTTP proxy. So take HTTP in, send HTTP out. These can be standard interfaces that we can ship, everybody can align on, and then target in their individual language tool chains. And then from this, another set of, what we were solving in Wasm Cloud in our own way, but what we really wanted was for different microservices to be able to interop with each other. And so an extension of this complex types proposal came the component model, which is essentially just wrapping the core piece of compute, which is a WebAssembly binary, a WebAssembly module, with a little metadata that details the complex types that are going to go across the ABI. This is the component model. There are functions that you can import and export from WebAssembly. Think of it like providing an API or calling an API. And under the hood, it's just core Wasm, like WebAssembly 1.0. This allows you to do language interop, to have strictly defined interfaces, and potentially under the hood, most importantly, have a segmented piece of memory where you own your own stack. You are not sharing memory between untrusted pieces of compute, and so it's not violating the WebAssembly sandbox. And when you look at all of this, and this is when we started looking at WASI, and we're like, wow, like that solves a lot of our problems. That solves a lot of the things that we've been running into issues for, and we had to munge a couple things. But interface types in the component model covers the issues that we were having with IDLs and generating SDKs and making our own protocol. And so about a year ago today, and I say about because I think it was like next week it would be a year ago, we launched Wasm Cloud 1.0. So from 2019 to 2024, we had been working on this, doing a lot of churn. 2024, we launched Wasm Cloud 1.0. And this is when we brought in WASI 0.2 as the supported WebAssembly target. So we didn't need to focus on WAPC, writing our own Smithy interfaces, doing codegen, making our own RPC protocol that has proprietary things. We adopted the WebAssembly standard alongside some of the other things that we had already been working on, like OTEL for all observability, Open Application Model for like our declarative application spec, Cloud Events for all informational events. The CNCF Wasm working group published recommendations for distributing WebAssembly via OCI, and that's pretty much the standard for how people do it now. We were able to take these things from the standard and implement that to make our lives easier. We get to spend time on what differentiates us as a project. And this was the hardest lesson for us to learn at the time because we weren't very involved with WebAssembly standards. We were doing our own thing. We were writing our own protocol. It was working for us. We had control. But if we had gotten in the beginning, joined the community groups, joined the people working on the standards, offered our feedback, we had real people running this in production, we could have pushed the standard along. It could have gone quicker. I'm not saying that we are like the best WebAssembly people ever and we would have made it all awesome, but we would have been at the table and airing some of the things that we had problems instead of just like working around it and like building our whole thing. And ultimately, all these Wasm projects that are doing the same thing, competing on these like table stakes, like just make it work, it just hurts the ecosystem. Everybody's doing their own thing. It doesn't really match up. And you can only get really so far making your own protocols. And, regardless if you're doing Wasm, this is the maintainer track. Everybody here can wrestle with the same problem of building too many things. This is the, everybody's favorite image. But after all, we're here at this cloud native conference. Like all of these projects exist, have some base, some Kubernetes story, like things, the OpenTelemetry, like all these standards that we've kind of aligned on makes for this ecosystem of projects that interop. We use the same things. We can knowledge transfer. I call that Wasm Cloud on there because we're over there. All of those things, and it's the same for WebAssembly, same for cloud native, and ultimately for Wasm Cloud 1.0, we like rewrote the whole thing. We rewrote our host to target the standard, and it's actually, I want to say that it's actually okay to do that. It's okay for you to take something that you were doing in your own way for a long time, something else has come along and say, you know what, we can just get further if we don't do that. And the way that we talk about this internally at Cosmonic and for Wasm Cloud is in terms of innovation tokens. You get a certain number of innovation tokens when you're working on a new project or when you're working on an existing project to do special fun things that you think are fun, choosing your language. You can write everything in Pony or whatever, but you only get a certain number of those before people start getting alienated, people can't understand what you're doing, or people get locked into your platform. So, if there's anything I can urge you to walk away from this talk with, it's that, think about the things that you're building and what you really want to do with your project. Are you spending your innovation tokens on the things that make you better and make you special and make people enjoy using your thing? Or are you writing a binary FFI protocol so that your thing can just work? And really, at the end of the day, WasmCloud has its project goals. We want developers to be more productive. We want developers to have fun writing microservices. We don't want developers to be spending 60% of their time maintaining the things that they already wrote. We want people to just write code, prod at it, test it, and then deploy it to production, and then leave it there. And that would be great. I would have a great time if that was my life. And that's why I love working on WasmCloud. That's what the project is designed to do, not to be the coolest WebAssembly thing. It's technology and standards are what make our project possible. I want to just give a quick acknowledgement, if you're watching, to Phil Keaty and Kevin Hoffman. These are two original visionaries behind WAPC, WasmCloud. They were great mentors to me coming out as an early developer at Capital One and working on open source. And a huge shout out to everyone who's contributed, the hundreds of people who have worked on WasmCloud over the years. Thank you for your patience. I'm glad we're on the track that we're on now. And I thank you all for coming to this talk. I have a couple minutes for questions if you have anything. Oh yeah, if you do have anything, there's a little mic over there, so you don't have to shout at me. All right, folks. Well, I'm going to be hanging around afterwards, too, if you are feeling shy and don't want it on the recording. But any questions are welcome. But thank you all. Have a great conference. I really appreciate it.